Bismillahirrahmanirrahim. Assalamu alaikum dear students. Our today's topic is again probability from chapter number 2. Let's have more details about probability. Learning objectives are the students will be able to define and elaborate the types of probability, to explain the simple rules of probability, to understand the real-life problems involving probability, and to solve simple numerical problems of probability. Let's recall what is probability. The word probability is derived from the Greek letter meant as approval. So probability is the chance that something will happen or how likely it is that some event will happen. Sometimes we use a numerical number to measure probability when we say there are 10% chances of rain, or we use the vocabulary of probability when we make use of the words impossible, unlikely, possible, even chance, likely, and certain. For example, it is unlikely to rain tomorrow. On a probability scale, if an event is impossible, then probability is 0, and an event with a low probability is unlikely to occur, whereas an event with a high probability is likely to occur. For example, in a draw of a fair cubical die, the probability of getting one dot is 1 by 6, which is a low probability, so it is unlikely to occur. Whereas in drawing a blue ball from a bag containing 5 balls is 4 out of 5, which is likely to occur and has a high probability. If an event is sure to occur, then its probability is equal to 1. The events with even chance have 50% probability for head and 50% probability for tails, the two faces of a coin. When we toss a coin, there are two possible outcomes, 1 by 2 chances for heads and 1 by 2 chances for tails, so they have an even chance of occurrence. Definitions of probability. Usually, probability of an event is defined in any one of the following two approaches. Number 1, subjective approach, and number 2, objective approach. Subjective approach is based on personal judgment or degree of rational belief in the occurrence of an event. For example, the belief that it will rain today. Whereas objective approach consists of 3 types of approaches: classical approach, frequency approach, and axiomatic approach. Subjective approach. In subjective approach, the probability of an event is defined as the measure of the extent of belief in the occurrence of an event by a particular person. Probability in this approach is purely depending on the thinking or the evidence available to a particular person. That is why this approach is also known as personalistic approach. The disadvantage of this definition is that different persons may find different probability for the same event, even though they have same evidences. Subjective approach is applicable to real-world situations like business, economics, etc. Objective approach. In objective approach, the probability of an event is defined in 3 ways. Number 1 is classical or mathematical or priori definition of probability. In mathematical our classical sense, the probability of an event is defined as if there are n equally likely and mutually exclusive outcomes of a random experiment, and m of these outcomes are favorable to the occurrence of an event A, then probability of the occurrence of A is equal to the ratio m over n. That is, probability of A is equal to number of favorable outcomes of an event A divided by the total possible outcomes in the sample space S. Favorable outcomes to A divided by total possible outcomes, which is m over n. In this approach, we assume that an experiment or trial results in any one of the many possible outcomes. Each outcome belongs equiprobable or equally likely outcomes. And this definition was given by P.S. Laplace. The classical definition is criticized on the following grounds. The term equally likely used in the definition means equally probable. Thus, the definition is circular. That is, it defines probability in terms of itself. In some problems, it is not possible to enumerate the number of possible outcomes because they are infinite. This definition fails when the assumption of equally likely outcomes is not fulfilled. For example, when a coin or a die is loaded, that is not fair. Statistical relative frequency or posteriori definition. In this approach, probability is obtained by actually performing the experiment large number of times. As the number of trials n increases, we get more accurate results. The relative frequency approach to define probability depends on the repeatability of some process and the ability to count the number of repetitions, as well as the number of times the event of interest occurs. In this context, we may define the probability of observing some characteristic A as an event in the following terms. Definition: if m is the number of occurrence of event A in large number of trials, say n trials, then the probability of occurrence of event A, P of A, is the relative frequency of m and n, as the number of trials grows infinitely large. Mathematically, probability of A equal to limit n tends to infinity m over n. Of course, we cannot observe an infinitely large number of trials. This theoretical constraint is interpreted to mean that as n becomes larger, the relative frequency becomes stable. There may be two extreme cases. If there is not any favorable outcome for the occurrence of an event A, then m equal to 0 and probability of A is equal to 0. That is, probability of A equal to m over n, where m is equal to 0, so 0 over n equal to 0. And if all the possible outcomes are favorable for the occurrence of event A, then m equal to n and probability of A is equal to 1. That is, probability of A equal to m over n, where m is equal to n, so n over n equal to 1. When probability of A equal to 0, in this situation the event A is called an impossible event or completely unsure event, and we may write probability of A equal to probability of an empty set which is equal to 0. And in this situation, when probability of A equals 1, the event A is called certain event or sure event, and we may write probability of A equal to probability of sure event S equals 1. These two extreme cases suggest that the probability lies between 0 and 1. The above definition is criticized on the following grounds. It is difficult to ensure that the experiment is repeated under uniform conditions, and in the real world, the experiment can be repeated only a finite number of times, not an infinite number of times. Due to shortcomings occurring in the classical and relative frequency definitions, axiomatic definition was proposed by Russian mathematician A.N. Kolmogorov in 1933, where axioms are statements which are reasonably true and are accepted by everyone without seeking any proof. Axiomatic definition of probability is: in this approach, the probability that an event A will occur is a number P of A assigned to this event. This number satisfies the following axioms. Let S be the sample space associated with a random experiment. Let A be the event in sample space S. Then probability of A is the probability of occurrence of A if the following axioms are satisfied. Number 1. For every event A, probability of A greater than or equal to 0 but less than or equal to 1. That is, probability of A lies between 0 and 1. So negative probability has no meaning. Second, probability of the sure event S equal to 1. The probability of an event sure to occur is 1. Number 3, if two events A and B are mutually exclusive events, then probability of A union B is equal to probability of A plus probability of B. Some important probability rules are listed here. Number 1, the probability of an event is between 0 and 1. A probability of 1 is equivalent to 100% certainty. Probabilities can be expressed as fractions, decimals, or percents. So probability of an event A lies between 0 and 1. Second rule is the sum of the probabilities of all possible outcomes is 1 or 100%. If A, B and C are the only possible outcomes, then probability of A plus probability of B plus probability of C is equal to 1. Sum of all the three events is equal to 1. For example, a bag contains 5 red marbles, 3 blue marbles and 2 green marbles. Then probability of red marbles plus probability of blue marbles plus probability of green marbles is equal to 1. Now probability of red marbles is 5 out of 10. There are total 10 marbles and out of 10 red marbles are 5. So probability of red marbles is 5 by 10 plus probability of blue marbles is 3 out of 10 and probability of green marbles is 2 out of 10. So 5 by 10 plus 3 by 10 plus 2 by 10 is equal to 10 by 10, which is equal to 1. The third probability rule is the sum of the probability of an event occurring and of not occurring is 1. That is, probability of event A plus probability of event not A is equal to 1. Or we can say probability of not A is equal to 1 minus probability of A. Probability of not A is equal to probability of A complement. For example, a bag contains 5 red marbles, 3 blue marbles and 2 green marbles. Then probability of red plus probability of not red is equal to 1. Probability of red is 5 by 10 and probability of not red, which are blue or green marbles, is equal to 1. For example, 5 by 10 plus 3 by 10 plus 2 by 10 is equal to 1. Probability of not red is equal to 1 minus 5 by 10 is equal to 5 by 10. fourth rule is, if two events A and B are independent, this means that the occurrence of A has no impact at all on whether B occurs and vice versa. Then the probability of A and B occurring is the product of their individual probabilities. That is, probability of A and B is equal to probability of A multiplied by probability of B. If the two events A and B are independent, then their combined probability is equal to the product of their individual probabilities. For example, in a roll of a die and a flip of a coin, probability of heads and roll a 3 dots is equal to probability of head multiplied by probability of 3 dots. Probability of head when we flip a coin is 1 by 2, and probability of getting 3 dots when we roll a die is 1 by 6. So the product of 1 by 2 and 1 by 6 is equal to 1 by 12, which is the probability of head and a roll of 3 dots. Rule number 5 is, if two events A and B are mutually exclusive, meaning A cannot occur at the same time as B occurs, then the probability of either A or B occurring is the sum of their individual probabilities. That is, probability of A or B is equal to probability of A plus probability of B. For example, a bag contains 5 red marbles, 3 blue marbles, and 2 green marbles. Probability of red or green is equal to probability of red marbles plus probability of green marbles, which is equal to 5 by 10, which is the probability of red marbles, plus 2 by 10, which is the probability of green marbles. So the sum of these two equal to 7 by 10. Rule number 6 is, if two events A and B are not mutually exclusive events, meaning it is possible that A and B occur at the same time, then the probability of either A or B occurring is the sum of their individual probabilities minus the probability of both A and B occurring. Probability of A or B is equal to probability of A plus probability of B minus probability of A and B together. Example, there are 20 people in the room, 12 girls, 5 with blonde hair and 7 with brown hair, and 8 boys, 4 with blonde hair and 4 with brown hair. There are a total of 9 blondes and 11 with brown hair. One person from the group is chosen randomly. Probability of a girl or blonde is equal to probability of girl plus probability of blonde minus probability of girl and blonde. Now probability of girl, as we know, is 12 out of 20. Since there are 12 girls and total 20 people in the room, so the probability of a girl is 12 out of 20. Probability of blonde, there are total 9 blondes, so 9 out of 20 minus 5 out of 20, which is the probability of a girl and a blonde. As we counted 5 girls in this number 9, so we subtract 5 out of 20. Solving these probabilities, we get 16 over 20. Rule number 7 is, the probability of at least one event occurring out of multiple events is equal to 1 minus the probability of none of the events occurring. Probability of at least one is equal to probability of none. Example, roll a coin 4 times. What is the probability of getting at least one head on the 4 rolls? Earlier you learned how to construct a sample space when a coin is tossed 4 times. 2 raised to power n equal to 2 raised to power 4 equal to 16 possible outcomes for a sample space when we toss a coin 4 times or 4 coins are tossed once. So probability of getting at least one head is equal to 1 minus probability of no head. No head means all tails. Probability of tails on 4 tosses is equal to 1 by 16. So 1 minus 1 by 16 is equal to 15 by 16. In other words, we can say 1 minus probability of tail, tail, tail and tail. 1 minus probability of tail on the first trial multiplied by probability of tail on the second trial multiplied by probability of tail on the third trial multiplied by probability of a tail on the fourth trial. So product of these 4 probabilities is 1 by 16. 1 minus 1 by 16 is equal to 15 by 16. Rule number 8 is, if event B is a subset of event A, then the probability of B is less than or equal to the probability of A. If B is subset of A, that is A contains B, then probability of B is less than or equal to probability of A. For example, there are 20 people in the room, 12 girls and 8 boys. 12 girls, 5 with blonde hair and 7 with brown hair, and 8 boys, 4 with blonde hair and 4 with brown hair. Now probability of a girl with brown hair is less than or equal to probability of girl. Probability of girl with brown hair. There are total 7 girls out of 20 with brown hair. 7 out of 20 is the probability of a girl with brown hair. And probability of girl is, since there are total 12 girls out of 20 people, so 12 over 20 is the probability of a girl. So 7 over 20 is less than or equal to 12 over 20. It means probability of a girl with brown hair is less than the probability of a girl 12 over 20. Simple numerical problems of probability. Example number 1. If a coin is tossed, what is the probability of a head? When we toss a coin, the number of sampling points in the sample space is 2 raised to power n. This is the formula for getting number of sampling points in the sample space when a coin is tossed. 2 is meant for 2 faces, head and tail, and n is for number of coins or number of tosses. In this example, n is equal to 1, so 2 raised to power 1 equals 2. There are 2 possible outcomes, head and tail, in the sample space S. Let A denote that heads occurs, then A equal to H. We are interested in heads, so the outcome of interest A is equal to H. Favorable cases are 1. Probability of event A equal to favorable outcomes divided by total possible outcomes, which is equal to 1 by 2 and is equal to 0.5. Example number 2. A fair coin is tossed twice. What is the probability that one head occurs? When 2 coins are tossed, the formula for getting number of sampling points in the sample space is 2 raised to power n, which is equal to 2 power 2. N denotes the number of tosses or number of coins, and base 2 denotes the number of faces, the 2 faces of the coin. 2 raised to power 2 equal to 4. So sample space will consist of 4 possible outcomes, HH, HT, TH and TT. Let A denotes the event that exactly one head occurs, then A equal to HT and TH, the 2 possible outcomes. So favorable outcomes to the event A equal to 2 and probability of A equal to favorable outcomes divided by total possible outcomes. 2 over 4 equal to 0.5. Example 3. 3 fair coins are tossed once. Find the probability of exactly 2 tails, at least 2 tails, at most 2 heads. When 3 fair coins are tossed, the formula for getting number of points in the sample space is 2 raised to power n equal to 2 power 3. N is equal to 3 in this example. So 2 power 3 equal to 8. The 8 possible outcomes are HHH, HHT, HTH, HTT, THH, THT, TTH and TTT. You are already familiar with construction of sample space when 3 fair kinds are tossed. Now let A denotes exactly 2 tails. Then A will consist of outcomes with 2 tails, HTT, THT and TTH. Number of favorable outcomes are 3. Probability of A equal to number of favorable outcomes to the event A divided by number of total possible outcomes in the sample space, which is equal to 3 by 8 and is equal to 0.375. In the second part, let B denotes at least 2 tails. In this part, we are interested in at least 2 tails. At least 2 tails means 2 or more tails. So B denotes the events HTT, THT, TTH and TTT. There are 4 possible outcomes in the event B. Probability of B is equal to favorable outcomes to the event B divided by total possible outcomes, which is 4 over 8 and is equal to 0.5. In the third part, let C denotes at most 2 heads. At most 2 heads means 0 head, 1 head or maximum 2 heads and not 3 heads. So C will consist of HHT, HTH, HTT, THH, THT, TTH and TTT. Number of favorable outcomes in the samples in the set C is 7 and number of possible outcomes in the sample space is 8. So dividing 7 and 8 we get 0.875, which is the probability of the event C. Example number 4. If a die is rolled, what is the probability that the number appearing on the top is an odd number, an even number less than 5? For a die throwing experiment, number of sampling points in the sample space, the formula is 6 raised to power n. 6 is meant for 6 faces of a die and n is for number of dice or number of throws of a die. In this example, n is equal to 1, so 6 raised to power 1 equal to 6. Sample space will consist of 6 possible outcomes: 1 dart, 2 darts, 3 darts, 4 darts, 5 darts and 6 darts. In the first part, let A denotes an odd number. Then A will consist of the odd outcomes 1, 3 and 5. So number of favorable outcomes in the event A is 3. Probability of A equal to number of favorable outcomes to the event A divided by total possible outcomes, which is equal to 3 by 6 and is equal to 0.5. In the second part, let B denotes an even number less than 5. There are 3 even numbers 2, 4 and 6, and less than 5 there are 2 even numbers 2 and 4. So B consists of 2 and 4. Number of points in the B event is 2. Probability of B is equal to number of favorable cases to the event B divided by total possible outcomes in the sample space S, which is 2 over 6 and is equal to 0.333. Example number 5. 2 fair dice are rolled once. What is the probability that the total score is 8, score is at least 10, 5 occurs on second die? For 2 dice, number of sampling points in the sample space is 6 raised to power n equal to 6 power 2. Here n is equal to 2. So 6 power 2 equal to 36. The sample space will consist of 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6 and so on. 6, 1, 6, 2, 6, 3, 6, 4, 6, 5 and 6, 6. You are already familiar with the construction of sample space in case of two fair dice are thrown. Let A denotes the total score is 8. Then, looking at the outcomes of the sample space, we can see that the outcome 2, 6, 3, 5, 4, 4, 5, 3 and 6, 2 scores total 8. So A set consists of 2, 6, 3, 5, 4, 4, 5, 3, 6, 2. Number of sampling points in the event A is equal to 5. Favorable outcomes are 5. So probability of event A equal to favorable outcomes over total possible outcomes. 5 over 36, which is equal to 0.1389. In the second part, let B denotes that score is at least 10. At least 10 means 10, 11 or 12. Then B will consist of 4, 6, 5, 5, 6, 4 for 10, 5, 6 and 6, 5 for the event 11 and 6, 6 for the score 12. So B set will consist of 6 possible outcomes. Favorable outcomes to the event B is 6. Probability of B is equal to favorable outcomes to the event B divided by total possible outcomes in the sample space, which is equal to 6 divided by 36 and is equal to 0.1667. In the third part, let C denotes that 5 occurs on the second die. Then C will consist of 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, 5. In each of these outcomes, on the second die, 5 occurs, and on the first die, 1, 2, 3, 4, 5, 6 possible outcomes occur. Total number of points in the set C is 6. So favorable cases are 6. Probability of C is equal to number of favorable outcomes to the event C divided by total possible outcomes in the sample space S, which is equal to 6 over 36. Simplifying this fraction, we get 0.1667. Example number 6. If two fair dice are rolled, then obtain the probability that the sum of darts shown on the two dice is 7, 4 or 11, odd, even or multiple of 3. When two fair dice are thrown, number of sampling points in the sample space are 6 power n equal to 6 power 2, which is 36. Now, how to construct sample space for the sum of darts is, in a two-way table, first die has 6 faces, second die has 6 faces, so add 1 plus 1, 2, then 1 plus 2, 3, 1 plus 3, 4, 1 plus 4, 5, 1 plus 5, 6, 1 plus 6, 7. Similarly, 2 plus 1 is 3, 2 plus 2 is 4, 2 plus 3 is 5, 2 plus 4 is 6, 2 plus 5 is 7, 2 plus 6 is 8. That is the sum of darts on the upper faces of the two dice. So minimum sum will be 2 and maximum sum will be 12. The sum will vary between 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. Between 2 and 12. Now this is the sample space for sum of darts from 2 to 12. In the first part, let A denotes the sum of darts is 7. Now looking at the table, we see that the outcome 7 is 1, 2, 3, 4, 5 and 6 times. The outcome 7 is repeated 6 times. So favorable outcomes to the event 7 is 6 and probability of A equal to favorable outcomes divided by total possible outcomes, which is equal to 6 over 36 and is 0.1667. In the second part, let B denote sum of darts is 4 or 11. Now we are interested in sum is 4 or the sum is 11. The sum is 4 is shown in this table 4, 4 and 4 3 times, and sum 11 is 2 times 11 and 11. So 3 outcomes of 4 plus 2 outcomes of 11. Total favorable outcomes are 5. Number of favorable outcomes to the event B is 3 plus 2 equal to 5. Probability of B is equal to favorable outcomes to the event B divided by total possible outcomes in the sample space S, which is equal to 5 over 36. Simplifying this fraction, we get 0.1389. In the third part, let C denotes the sum is odd. Let's see the sample space. The sum is odd. The odd numbers are 2 is even, 3 is odd, 4 is even, 5 is odd, 6 is even number, 7 is odd. So the odd numbers are 3, 5 and 7. We count the number of 3's, we will count the number of 5's, then we will count the number of 7's, and then we count the number of 9's, and then we count the number of 11's. So there are total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 and 18. Out of 36 outcomes, there are 18 odd outcomes. So number of favorable outcomes is 18. Probability of C is equal to number of favorable outcomes to the event C divided by total possible outcomes in the sample space S, which is 18 over 36 and is equal to 0.5. Similarly, let D denotes the sum is even. Since there are 18 odd numbers in the sample space, so remaining 18 are even numbers. In this case also, the favorable outcomes are 18 and total possible outcomes are 36. So probability of D is equal to 18 over 36, which is equal to 0.5. In the fifth part, let E denotes the sum is multiple of 3. Let's see the sample space. Multiples of 3, the outcome 3, then 6, then 9 and 12. These are the multiples of 3. So 3 is repeated 2 times, 6 is repeated 5 times, 9 is repeated 4 times and 12 is only once. So the possible outcomes in the sample space E, where E denotes the sum is multiple of 3, is 12. So probability of E is equal to number of favorable outcomes to the event E divided by total possible outcomes, which is equal to 12 over 36. Simplifying this fraction, we get 0.333, which is the probability of the sum is multiple of 3. Thank you. Have a nice day.